Okay, so this is the single slit intensity video. This is actually take 3. I've been interrupted 3 times by a cat, so hopefully this won't happen with this one. So with this, we're going to look at the single slit intensity graphs. We're going to look at the interference pattern and how it changes with different types of monochromatic light. We're also going to look at how it would look with white light. And we're also going to talk about how the equation works. So first of all, for the IB, we don't actually have to explain why we get the single slit interference pattern, but it is good to kind of recap and go over the reasoning that we get these different interference patterns. So we have the diffraction, we get areas of constructive and destructive interference. So when we're dealing with a single slit, we actually use Huygens principle. This does not get assessed on your exam, but with Huygens principle, we imagine that the waves approaching are a series of little wavelets, and those wavelets each have their own diffraction, which is why we still get those areas of constructive and destructive interference, which is why we still get an interference pattern happening. Okay, so remember, areas of constructive interference, areas of destructive interference lead towards our maxima and our minima. So with this, we start looking at the key kind of characteristics of our single slit intensity pattern. So if I had intensity, and I'm going to start drawing my intensity patterns on here. So our central maxima, okay, so our 0 order, is going to be the most intense, and you should have seen that if you were using the lasers in the classroom, that you have a really bright central maxima. Okay, our subsequent maximas are much less intense. Okay, the first maxima actually after the central, okay, so this is 0 order, this is our first order, is actually only 5% of the intensity. But to draw 5% on a diagram is really difficult, so we normally show it to be about a quarter of it or less. Okay, please don't be making them any bigger if you have to draw these than a quarter of that first central maxima. The other thing that you may notice as well is that that central maxima, okay, that central fringe, if you've been looking at it with your laser pen as well, is much thicker than the subsequent maximas that are appearing. In fact, it's double it. So by eyesight, you need to make sure that your first maxima is about half the size of your central maxima. Okay, so if you can see here, if this one was a width of x, okay, the central maxima is actually going to be 2x. Okay, so 2 little things that you therefore need to watch out for if you are drawing these on here. Okay, so that's in terms of drawing our intensity graphs. That's what we want to make sure we are looking out for. So then leading on to the equation, so we're going to be dealing with these angles, and we're going to be dealing with the angle, and it's the angle towards the first minima. Okay, so being really important, this is the angle to the first minima. Okay, so our first destructive interference, so you should be able to see down here. Okay, so that is our angle towards that first minima. Lambda is the wavelength, and B is the slit width. Okay, this is actually a simplified equation, which comes from d sine theta is equal to n lambda, which is something that we use with diffraction gratings, which is going to be covered later on, but this is a simplified version of that equation. So just kind of bearing in mind that theta is the angle to the first minima, okay? So we start then looking at what this might mean, okay? If I had my B in there, if I start looking what a large angle would mean, okay, a large angle basically means that this is going to be coming out much further, so I'm going to have a much larger, if I just move this up a little bit, I'm going to have a much wider central maxima. So if theta is greater, okay, my interference pattern is going to be more spread out. Okay, so that minima, that first minima, would occur at a larger distance, so that I'd have a much thicker central maxima. A smaller theta then also means that we have a less wide, so a thinner central maxima. So sometimes they might do this in a way that they start asking you questions to describe the interference pattern. So they'd ask you what would be changing here. So we're going to start looking at what this means in the next one, because it says, can you qualitatively describe about the single slit interference patterns? So if we start looking, what would happen if we increase the slit width? So if I made that B, okay, a greater B, or if I had a really small B coming through there. So I start thinking, well, if I increase the slit width, so I'm going to make B larger. If I make B larger, okay, what that actually is doing is that's making my theta smaller. It's making my angle much smaller. Okay, so the angle to the first minima is decreasing, which means my maxima are going to become thinner. So rather than having a kind of more spread out, we would end up with a much narrower interference pattern coming on here, because my angle is going to be much smaller. The other sometimes they like to link it to is in terms of wavelengths. So they might give you different wavelengths and ask to describe them. They often ask you to do this in terms of different light. Okay, so they have to ask you maybe with monochromatic light what you would see. So again, we start looking at theta. And again, if I increase the wavelength, so light of larger wavelengths such as red, okay, if I increase the wavelength, I'm going to be increasing the angle to the first minima. Okay, so remember, you want to make sure you mention that in the question. Don't just say about increasing the angle, it's increasing the angle to the first minima, okay, which means that we're spreading it out, so the maxima are going to become wider. Again, if I decrease the wavelength, I'm going to do the opposite. So again, we look at red light compared to blue light. If we look at the red light, we can see that we have a much larger, wider, so a much wider central maxima, okay, because my angle, all right, from the slit is going a greater angle, so I'm going to occur my first minima at a further distance, whereas the blue light, so I wasn't explained very clearly then, my blue light, okay, my theta is going to be smaller, so the first minima is going to be much closer towards that central maxima, and so therefore I have a thinner interference pattern here. They then ask you that you can also describe this for white light. So what we start thinking here is if we were having all of these waves, because white light, remember, in the visible light spectrum is all of our colours, so our Roy G. Biv. Okay, and again, thinking that our red is the longest going into violet. Well, if we look at our first order, they're all going to be reaching at the same point. Okay, so we're still going to have a central white maxima because all my different colours overlap to give me that white central maxima. Okay, we then would potentially still have these sort of dark fringes, but actually they don't really, aren't really being able to be seen. Okay, so next to kind of where our white would go, we then actually start to see our violet. Okay, and it's really important that it goes from violet all the way to red. So again, hopefully you saw this in class, and that violet was the first one and red was the wide one. We start thinking, well, why does that come in? Because it might be an explain question. So the central maxima, all of our waves are occurring in the same spot, so we get white light. Okay, and then the next one that's going to occur, because it's closer, okay, think of it having a smaller wavelength. I'm very sorry about that, because it's got a smaller, it's got a smaller wavelength, so it's got a smaller angle, is violet. So violet is going to occur first. Okay, now normally we don't actually see those minima appearing because the violet has already gone through towards the edge of that central white. Okay, again, then blue would be the next, then green, and then red, okay, being our longest wavelength. Okay, so that's going to be our biggest angle away from that central maxima for our first minima to occur, means that our red light is going to be the furthest away from our central maxima. Okay, so when you are explaining, okay, about a white pattern, so a white light pattern, you would talk about having a central maxima that is white, and the subsequent maxima will go from violet to red. The reason because violet has a smaller wavelength, and so the theta is going to be smaller, and so it's going to be closer to the central maxima, which is why it appears first. Red, you can use the counter argument, and sometimes, especially if it's a longer mark question, I usually try and give both. Okay, the red has a longer wavelength, therefore it's got a longer a larger angle, so therefore it's going to have a angle, so therefore it's going to be further away from the central maxima for its first minima to occur. So if we're kind of looking at this, we can imagine those are patterns happening. You can see that the violet one has occurred before the red one in terms of there, so the violet, and again it repeats on both sides. So we go out from central to violet, leading out towards red at the edge, and then we still get those repetitions. Again, I've just drawn in the minima there just as an example to show you that it's like the minima that's occurring, but really we don't actually see those minima, again, which you saw in class. So I hope that helps. I'm sorry about the cat jumping